to Robot Lab live event from University of Surrey campus. I'm the head of the lab, Professor Yang Gao. The rest are our team members who are supporting the demo today for you.
My name is Sam. I'm a postdoc researcher on orbital robotic.
Hi everybody, Alexander is here. I'm a lab technician. I'm responsible for maintaining hardware running and help Sam with his research.
I'm Rohit Nikam, a postgraduate student in space engineering, and basically I'm doing a technical support role to support some projects.
My name is Lisa. I'm an undergraduate in MEng Aerospace Engineering, and I'm a summer intern here at the Star Lab working on the robotics optical test bed.
My team, they're going to move to the demo station and start the preparation of the work. Thank you guys, see you in a bit. So now I'm going to first of all using this model here to help explain the space mission background that help describe and help you to understand why artificial intelligence and robotics is a very critical technology that we're using to support these future missions. So here you're saying a spacecraft that represents future core piece of hardware for the missions, then they can help to deploy the base infrastructures for large space telescope. So instead of launching a monolithic space telescope, which is going to be expensive and bulky to do, we're able to launch those space mirrors in small pieces like a mirror segment, and with the help of robotic arms on board the future spacecraft, we can perform and peak place. So you can envisage that these robotic arms will be autonomously identify space mirror segments from the mother satellite and transport it to the base structure after it's been deployed, so they can then form a much larger scale space optics devices. And here we have a model of the mirror segment in almost the true size, so you can appreciate the real scale of the space mirror, and they will be sitting on top of structures like this. Again, it's almost in the real scale, and there is a part of the structure which contains a mechanical part for the docking mechanism to work. And the other half of the docking naturally will sit on any factor of the robotic arm deployed from a servicing satellite that can perform the identification of the mirror segment structure in real time in the space environment and perform the approaching and docking autonomously. And in this process, which is of course a very critical process during the mission, we have to rely on robotic vision, some autonomous AI-based algorithms to achieve this very successfully. And this is the phase of the mission we are trying to demonstrate to you in the laboratory today.
Hi everyone, I'm Sam. After a very concise and complete introduction by Professor Yang, I will go through the technicality of how our experiments works today, basically. So we have got two different segments here that we used for the autonomous AI-based guidance, navigation, and control and docking system here. So I have got the service arm on my right side, which is your left side on the screen, the white robot that you can see here. Instead of normal grippers and things that you see on the robots, we have got half of the docking system attached as the end effector to it. And on above that, we have got different sensory systems and cameras that basically we record and in a live mode and send data to our onboard computer for machine learning and AI-based recognition of the two QR codes that we have attached here. So basically, what our service arms does, read these QR code, find the exact orientation of these QR code, and we have got a translation and transformation that generates the exact path and distance that it needs to travel, and orientation basically that our service arm needs to travel to catch and do the docking. On my left side, we have got this segment of the mirror that Professor Young already showed you. Basically, the mirrors goes on top of that one here, and it has got half of the docking mechanism here as well. This robot is has got a very special system. Basically, we created a free drive and free movement on it in a way that you already saw how I'm using it, in a way that it mimics the microgravity condition in orbit. So basically, we assume that this part is already floating in orbit, and the service arm comes and sync itself with this part and do the docking in autonomous way. So that's basically everything from me. Let's see how the system works.
Right, so you can see now we're simulating the target object in orbit motion. The target arm is trying to recreate a typical motion in orbit. And this is a phase in the mission where we have to perform a rendezvous with the target in space, where the servicing satellite carrying the arm is going to rendezvous and synchronize its orbital motion with the target. And once that's completed, you can see that the servicing arm will start to initiate, and the visual system start to guide the servicing arm. And it's worth highlighting this is through a vision sensor that is very simple. It's a monocular vision system and supposed to run very fast on board the spacecraft. Many of you would appreciate that even the modern spacecraft have a very limited onboard processing power because all the hardware has to be radiation harnessed. So it's actually very limited in computation. And you can see that approaching was very successful under the robotic vision algorithm. And there's a further window being added now, which confirming that the physical, the mechanical interface and locking is also successfully conducted. It's very interesting to see those yellow or orange colored dots that was detected by our ground truthing system, which Sam introduced earlier. This again a reassurance that the precision accuracy has been successfully achieved for this docking process. So the mission typically at this stage will need to move to a stage that the robotic arm has to withdraw. So meaning it has to move together with the added object to its anti-effector. This is a stage called rigidization, and the reason my colleague is holding a part of the servicing arm is because for this particular arm, due to safety reasons, it has a physical switch. In the real mission, there will be some kind of electrical switch that would allow the servicing arm to withdraw the anti-effector now with additional extra parts. But you can see very well that the rigidization is very successful. It's all safe I think we need to move now to the Q&A part, and
there are two black and white markers around the right-hand side of the robot. Sam, would you like to take this one?
That's great. So basically, those two things that you see on the side of the robot are the QR codes. So they look like normal QR codes, but they have been especially designed and created and measured precisely to use as a fiducial marker. So our autonomous system actually read those QR codes, generate the specific orientation that associated with each of the QR codes, and measure the distance from the camera. And we have got the translation from the camera to the end effector that we know that how long and in what distance actually and direction move the robot to do the actual docking. So in our today experiment, we are using those QR codes on the side of the robot as the main reference for guidance, navigation, and control. Thank you.
So the question here relates to the recognition phase of that process. So this is very interesting. So it asks best tools to recognize objects. I presume when you say best tool, you might be referring to different type of algorithms to perform the object recognition. So typically that process needs to start with detection. So you have to first detect and then you recognize, so meaning compare what you detect with what's in your database. And then you can perform the navigation, relative navigation. So from my point of view, I think we, as a research lab, we have actually a library of solutions. Solutions could include the more classical methods. You could look at fiducial marker. You could look at feature-based techniques. There are a range of machine learning methods that allows you to do the recognition. So basically classifying your object. A space robot different from other yes, of course, fair enough. Well, I think the short answer is yes, because robots designed for space or the extreme environment in space has to really be able to survive the space environment in terms of harsh radiation and also extreme temperature. So meaning it have a very extreme temperature range. So it could be as very hot or very cold in extraterrestrial bodies such as Mars, unlike on Earth. So the hardware has to be built to survive those conditions. There's also tend to be vacuum where the robots has to survive, and the communication latency, which is a point actually maybe we kind of took for granted so far, but actually it's really worth mentioning. It's all autonomous. It's all the decisions made in real time, but this is because remote operation of space robot is actually quite unrealistic because of the communication latency. So Sam and others, do you want to add your own thoughts?
I'm gonna jump in front of camera again.
Actually, I was thinking Sam actually has a lot to say because he comes from a terrestrial robotics background, so he
yeah, but you said most of the thing about the specification. Yeah. The thing that I want to add is when you want to buy a robot here, you normally know what is the application, and there are quite a few companies that you go and choose between them. But in a space, it is not quite the similar situation. There are companies that manufacture robots for space, but you need to go with them and explain to them what you want to do. And normally they make it from scratch for that specific mission. So basically it is not just going to the shop and make a robot. for research or for industry or for manufacturing and come back home. So besides those space conditions, harsh conditions that the robot must survive, there are lots of other specifications and things that needs to be met before you have the robot. You need to know what is your exact payload, what is the length of the arms that you want to handle any operation in a space, and how you want to launch it. Basically, it is important because it needs to survive the launch condition as well, extreme acceleration and other stuff. So it is a very complicated decision. And as Yang said, yeah, they are very different from the robots that we normally use in manufacturing and in research. Yeah. Thank you.
So thank you so very much.
Thank you.
Okay, take care.